Looks like things are fine. Okay, cool. So I also, first off, thanks for the intro and for having us here. I also want to just really quickly introduce my teammate, Alan, who will also be giving the second half of today's presentation. Alan, if you want to, is in this room right now? Yes. So Alan, if you want to introduce yourself, we can unmute you and then we can go ahead and get started. How do we?
You just need to click on his account and unmute him.
Oh, I see. Oh, it's organizer. Okay, cool. Yep, Alan, you're unmuted.
Okay, yeah. Hi guys, my name is Alan. Thanks so much for having me. I'm working with Brian. I worked with him. I've been on the project the whole time, and I'm going to keep working for the next few months as well. And I've mostly been responsible for thinking about like all the like front end game design stuff. And I'll be talking for the second half about like just broadly how we do game design under the constraint of zk. And I'm currently I'm supposed to be a sophomore at Columbia, but I'm taking another gap year. So who knows what's going to happen to my schooling after this.
Cool. And we have one more team member in here, Scott. Scott currently is in chat, and I guess I'll just let him introduce himself real quickly as well. And then we'll go ahead and screen share our presentation that we've got for today. So I don't know how do we unmute participants? Sorry, I'm
no, it's okay, it's okay. It's okay. Who do you want to unmute?
Scott Moses Sonarto.
Hi. Hello, everyone.
Yeah. Oh, there we go.
Hello, everyone. My name is Scott. I do the smart contract development for Dark. I also think a lot about interoperability and like meta universe of like Dark Forest. And I'm currently like a sophomore student studying electrical engineering and computer science in Diablo Valley College.
Awesome. Thanks, everyone. So what we're going to be doing today is we are going to be talking about Dark Forest and some of our thoughts on how applied zk engineering can be used for decentralized gaming, in particular on Ethereum. So what I'm going to do is I'm going to go ahead and screen share a slideshow for today. Let's see. Oh, can not all participants screen share? I'm just trying to.
So you need to, because of the Zoom bomb, we unlock work different, so you need to allow them to share.
Oh, I see. So, sorry, how do I, would one of you guys mind allowing the other Brian Gu in the participants to share?
Spotlight video? I mean, sorry, I'm just trying to see I can do that. I mean, I'm going to make him co-host, I guess.
Yeah, perfect. So I can see, doesn't seem that I can share video from.
Oh, you should be able to share your screen. Below you have to share screen on the bottom of your.
Oh, I see. Perfect. Okay. Sorry for the technical difficulties, everyone.
Don't worry.
But I think we should all be good now. Okay, cool. So today, as we mentioned, we're going to be talking about Dark Forest, which is, for those of you who aren't familiar, a zero-knowledge real-time strategy game. So imagine something like StarCraft, say, but decentralized and on the blockchain and persistent. So to start off with, we're going to talk a little bit about why zk is useful in games and sort of the zero-knowledge construction that makes Dark Forest work. Afterwards, Alan's going to talk about some of the elements of world building and how we basically try to put together a full and hopefully compelling end-to-end game experience given the constraints of the Ethereum blockchain. And so he'll be discussing some of the tricks we use, like procedural generation and some lazy updating stuff to give the game a bit more of a real-time feel, even within the hard execution constraints of Ethereum. Cool. So first, to start off with, to explain why zk is interesting to begin with for blockchain gaming, we have to motivate this with the concept of complete and incomplete information games. For those of you who aren't familiar, the idea here is that all games can be categorized into roughly two types: complete information games and incomplete information games. Complete information games are going to be games like checkers or chess, where basically everybody is going to know the full state of the world at any given time. So, I can see your chess pieces, you can see my chess pieces, and there aren't any secrets. But on the other hand, incomplete information games are going to be games like poker or real-time strategy games, where basically there is some notion of private state that not all players may know. So for example, in poker, I have my hand, you have your hand, and we don't necessarily know what each other's cards are, at least not with certainty. So real-time strategy games are another extremely popular form of incomplete information games. So for example, StarCraft or Age of Empires or Civ, games in this genre are often going to be incomplete information games because they have a mechanic known that is frequently called a fog of war. What a fog of war is essentially the mechanic that says that you might be able to see your own base on a game map, but you might not know where your opponents are or what they're doing if you don't have vision of the areas that they occupy. So, I might not be very familiar with what units my opponent is producing, or even the relative locations of all of their units and their armies relative to my base. Another kind of game that is going to fall in the incomplete information category is going to be like open world persistent MMO games. So for those who are familiar with things like EVE Online, or even games like Minecraft Anarchy servers, these are games that are incomplete information because not everybody is going to know everything about the state of the world. And the reason why these MMO games are often going to be incomplete information is because incomplete information games allow for a much richer and more dynamic space of possible strategies. So, you can see things like deception or, betrayal or complex social dynamics, emergent player behaviors, conditional coordination. All of these things are only possible when information is a first-class resource and there's some sort of information asymmetry between the different players of the game. So we're very interested in building incomplete information games in multiplayer settings for this reason. Unfortunately, due to the nature of decentralized systems, most blockchain games and settings are necessarily complete information settings. So the reason for this is because, in some framing, a decentralized system is a system whose data layer is completely open and transparent, i.e. anyone can inspect the EVM state at any time and determine, the full contract state of any given decentralized app. So for example, CryptoKitties is a complete information game because it can be thought of as like a trading card game where everybody knows who owns what kitty and what all the properties of each kitty are. So naively, it seems like it would be really, really difficult to bake in this notion of incomplete information into the blockchain simply because, the data layer is completely open. However, it turns out that recent advancements in zk technology allow us to kind of hack in the notion of hidden information or information asymmetry into a blockchain setting. So to explain how this works and why zkSNARKs are useful, we've got this diagram over here. And the core idea is basically that players are going to be able to, like with zkSNARKs, players are able to keep private state, but commit sort of a hidden commitment, commit a public commitment to this hidden private state onto the network without revealing what that hidden state is, and then operate on that hidden state using zero-knowledge proofs. So to start off with, on the left, we've got some player who is holding some secret private state S1. Instead of uploading their private state up to the network, what the player is going to do is they're going to upload a public commitment. So let's say they're going to hash their private state and upload this C1 onto the network. Along with this, they're also going to upload a zero-knowledge proof that that hash does indeed correspond to some valid private state pre-image. So this is a ZK proof of knowledge of pre-image of a hash. Whenever the player wants to make a state transition, say from private state S1 to private state S2, what they're going to do is they're going to upload the hash of their new private state, as well as a zero-knowledge proof that there is a valid state transition going from the pre-image of their first commitment to the pre-image of their second commitment. So basically saying that, the state transition from S1 to S2 is indeed valid according to the rules of the game. So the network is never seeing S1 or S2, and kind of a concrete example of what this might be, what this proof might be saying in an incomplete information game is something like, this proof morally is going to claim something like, I moved my knight from some secret location A to some secret location B. I'm not going to tell you what A or B actually are, but this proof does indeed prove that my piece moved in an L shape. And because it's zero knowledge, it's going to reveal no other information about kind of like the underlying location of the piece. So with this kind of construction, we're basically able to do things that are a little bit more complicated than traditionally, we see a lot of like trading card games and other sorts of, complete information games on the blockchain. So now I guess we can get into sort of what Dark Forest is and how it works. This is just a screen cap from the game. And what we're going to be talking about sort of is how we use zero knowledge for incomplete information in Dark Forest. So Dark Forest, as we mentioned, is a real-time strategy game, and thematically it's sort of it's a space conquest game. So the goal is essentially, you, the player, are going to initialize on some home planet in a vast universe. And your goal over time is going to be to sort of expand your empire and conquer more planets. You may run into other players, you may engage in sort of space warfare with them, but this is kind of the premise, and it's a relatively simple game as far as mechanics go, but it is doing something kind of interesting with ZK under the hood. So in terms of the game construction, everybody is going to live on a large two-dimensional grid. And what we're going to say is that there's going to be planets at some of the coordinates x, y on this large grid. And for any location x, y, we're going to define that the public address of that location is the hash of x, y. So the coordinates themselves are going to be the location's private address, and all the contract is going to see, and the only thing that the network is going to see is the public ID or public address of these locations. Furthermore, we're going to specify, you'll notice that like not every like square here is occupied by a planet. Like planets are sort of scattered throughout space. Basically, the other thing that the Dark Forest core contract specifies is that the only planets that hash to under a certain difficulty threshold, only coordinates that hash to under a certain difficulty threshold are going to be considered habitable planets. All of their spaces are just kind of like empty space. And finally, player-controlled units and resources live on planets that players own. So real quick, let's talk a little bit about what in the game is considered public knowledge and what is considered private state. So the things that are stored on-chain are basically going to be which public IDs, like which public addresses of locations are owned, who owns them, and what resources and forces kind of exist at those addresses. But privately, we store what these locations actually are. So on the contract never sees any coordinate pairs or locations or anything like that. It just sees public addresses. And because hash functions are hard to invert, this means that anybody inspecting the contract state is not going to know by default where all the players actually are in the universe. But privately, in my browser's local storage, I'm going to be storing the coordinates x, y of all the different planets that I own and any information that I learn through computation. So what does information learned through computation mean? This is basically the central mechanic in Dark Forest, which is like the cryptographic fog of war that some of you might have seen in our blog posts. Well, concretely, let's suppose that the two of us are playing a very simple version of Dark Forest. Suppose that I initialize at some planet at like 5, 20. Well, what I'm going to do is I'm basically going to hash those coordinates 5, 20, and I'm going to upload that hash onto the blockchain. And it's just going to look like a string of bytes, right? That anybody can look at, but nobody can really invert to determine where I live. Let's say then that you join Dark Forest and you initialize at some planet at 3, 8, and then you're going to upload a hash. It's going to look like just a string of bytes to me. I'm going to have no idea where you are just on the basis of looking at the contract state. Well, if I want to find players or points of interest near me, then the best that I can do, because all of this is secured with a hash function, is to essentially brute force search the area around me. So, I'm at 5,20 and I'm interested in finding things near me. So I might do things like, I might hash like 6,20 and then 5,19 and then 4,21. And I'll just sort of explore around the area, and eventually I'm going to hash 3,8 if I go far out enough, and I'm going to get some string of bytes that I can compare to the contract and be like, oh, someone's already published this hash before, so because hash functions are deterministic, I know that they must live at 3,8. And just for a quick little demo of that, I have my own local version of Dark Forest pulled up here, and you can kind of see that one of the core mechanics is, my browser is going to gradually be exploring space over time. So right now my CPU is hashing these like 16 by 16 chunks of hashes and basically looking for planets and other players. And it looks like just before this, it was actually able to find this player. Someone just asked how large the universe is. The universe sort of expands as players join it. So in the last version of Dark Forest, I think the universe ended up being it's a circle with a radius of about 70,000 units. So, and you can kind of see the rate at which my computer can hash, which is about it's like 256. You can see like the stats over here. I'm hashing about 700 units per second. Cool. So yeah, so that's basically sort of the high level of the game construction. What I'm going to do real quick now is just dive into the actual zk circuits and zk proofs that are used. So in Dark Forest, there are 2 player actions that require zero-knowledge proofs. The first is to initialize into the universe, and the second is to move forces between different planets in the universe. So to initialize in the universe, basically what has to happen is, I'm going to like start off at some coordinate pair. In the previous example, I said 5,20. And then what I'm going to do is I'm going to send the hash of that starting coordinate. That's going to be basically like my home planet ID, as well as a zk proof that does indeed correspond to a valid home planet, whose location I'm going to keep secret. So the reason I have to do this zk proof is because if I don't, then I might be able to, like, a malicious player might basically be able to initialize at a location that's not actually valid. They might be able to just send some like random string of bytes up to the contract, and the contract, because locations are kept private, has no way of verifying that that's actually a valid place in the universe. So the function signature for initializing in the Dark Forest contract basically takes 3 input arguments. The first is the planet ID, so that's the hash of the planet coordinates. The second is the current world radius. So, as we saw in the sort of browser version, the universe is an ever-expanding circle, and players cannot initialize at any given time outside of this circle. This ensures that players just like don't initialize arbitrarily far away. And then the third argument here is going to be the zero-knowledge proof that that planet ID and that the player does indeed have knowledge of the pre-image of that planet ID, and that's within the world radius. So what does the zk proof check concretely? It checks that I know some coordinates x, y, such that the hash of x, y equals a planet ID, and x squared plus y squared is less than the square of the world radius. So we write all of our circuits in zkSNARK, which is a great language for zkSNARKs, zkSNARK circuits built by IDEN3. And this is sort of what a simplified version of the circuit looks like, which is also available in our code base. If you look at our GitHub organization, darkforest-eth, you'll be able to find all this stuff as well. So this is what the init circuit looks like. And just to kind of break down all the different parts that we mentioned before, the sort of beginning of the circuit, in the beginning of the circuit, we declare the inputs and the outputs. So basically, I have some private coordinate pair x, y. In this circuit, we're going to prove that the hash of x, y equals this output pub. And we're also going to prove that x squared plus y squared is less than the world radius r. We do these range proofs, which are basically saying that x squared plus y squared is indeed less than r squared. So we are like in bounds in the world. And we're also just going to do this check that x and y are both under 2 to the 32. And this basically helps prevent like overflow errors. For those who are a little bit more familiar with how the protocols for zk circuits work under the hood, all of these operations are essentially occurring like in a very large prime field. So we have to make sure that computations don't overflow by doing these range checks. And then finally, this component or this part of the circuit is going to basically say that the mimc hash, which is a snark-friendly hash function, the mimc hash of x comma y does indeed equal to pub, which is the planet ID. Our circuit for move is a little bit more complex, but is basically made from the same pieces. So the function signature for move is going to be, first, I'm going to pass in the planet ID I'm moving forces from. And then I'm going to be passing in the planet ID that I'm moving forces to. And then I'm going to pass the world radius in. And basically, the proof is going to show that, all of my, like the from planet and the to planet are indeed inbounds. And then finally, I'm going to pass the distance between the from planet and the to planet. And the reason we do this is because moves in Dark Forest cost resources and time that's essentially a function of distance. So if I try to move my forces between two planets that are really far away, then I have to pay a much higher cost and the move takes much longer. So yeah, the ZK proof in this case is going to prove, again, keep in mind that like the actual underlying coordinates of the from planet and the to planet are going to be kept secret. So the ZK proof here is going to prove that basically the hash of the from planet chords, I have knowledge of the hash of the, I have knowledge of the from planet chords, and the hash of those coordinates x1, y1 does indeed equal the from planet ID. The hash of the to planet chords x2 and y2 does indeed equal to the to planet ID. Also, the to planet is indeed within, it's like inbounds in the universe, so I'm not trying to move outside of that like big circle. And then finally, the distance between these two planets, x1 minus x2 squared plus y1 minus y2 squared, is indeed less than the square of that distance that I'm claiming is an upper bound on the distance between the two planets. So once again, you can see like this circuit's a little bit larger, but structurally it's pretty much the same. First, we declare all of our inputs and outputs. We've got the like secret coordinates x1, y1, x2, y2. We have the claimed world radius to say that we're moving in bounds of, that's r. And we have this other signal dist max, which is basically going to be the a claimed upper bound on the distance between our two secret locations. And then as our outputs, we also want to claim, we're claiming that basically the hash of x1, y1 equals pub1, and the hash of x2, y2 equals pub2. And that's to planet ID and from planet ID in the earlier slide. So similarly to last time, we have these range proofs that basically just show that everything is in bounds and that we're not overflowing the prime field. We have the distance proof that's basically going to say that the Euclidean distance between these two planets is indeed less than r squared. And finally, we once again have this proof of knowledge of the mimc hash preimages that show that these are valid planet IDs. They're not just like random strings of bytes that we're like pulling out of thin air. Cool. So at this point, I'm going to go ahead and hand it over to Alan, who will talk about how we actually try to use zero knowledge to inform the gameplay mechanics and how we try to build a fairly compelling game experience within the constraints of Ethereum. So I'll let Alan share his screen now.
Let's see. Is this good?
Yeah, I think that works.
Okay, sweet. So I'm going to talk a little bit about the kind of like constraints that we have and the kind of like first principles game design thinking that we've been trying to use. So the kind of like the space that we're working in is like pretty new. So there's a few quirks that we need to work around. And what we really don't want to do is we don't want to like just kind of like not think about this and then just like graft the zero knowledge on top of like another game. So in particular, so first we want to think about like what exactly is it that we want to build. So we want to be able to support infinite players, and we want a persistent world. So basically the kind of model here is we want it to be like a de facto Dark Forest universe. So there's like, if anyone in the world wants to like play the game called Dark Forest, and they can kind of like log into the Dark Forest universe as opposed to like they spin up an instance. So a counterexample to this might be like traditionally in an MMO like World of Warcraft, you have like different servers and each server handles like, say like a few hundred players. So this is not what we want. We also want to build a real-time game, and we want to have diverse and meaningful content. So what does this mean? Well, we want to have meaningful content in the sense that there's like a lot of stuff to do and all of it like means something. It's like very different. So a counterexample might be like, well, so like we have, like we don't want to build a game which is just like entirely full of like collectibles. Or if any of you have heard of No Man's Sky, in early versions of No Man's Sky, there's just like a lot of planets to explore, but every planet is like functionally the same. And last of all, we want to build a fun game. So we don't want to just build like a technical flex or like something that like explores zero knowledge proofs. We want to build something that's like actually fun for people to play. Now, doing this is a little bit difficult because we're constrained by some set of things. So in particular, well, we have gas fees. Like currently on mainnet, it's like 50 cents to $1 for a transaction. And this just means that like pretty much no matter what we do, it's gonna require some sort of microtransactions. And this has some like specific consequences that we basically like want to avoid, making sure that like there's some world where the game that we build is very pay to win, and that's not what we want. We're also limited by block times. So it takes 3 to 15 seconds for like anything to go through Ethereum, which means that like if we want to build a real-time game, we have to look for ways around this because there's going to be like a 15-second delay between moves. We also have the zero knowledge construction that Brian described earlier, which means that we can never display coordinates on chain. Otherwise, this just like ruins the whole point. So coordinates have to be held off chain in the client. And we also have this weird limitation, which is that there's never going to be a ground truth client because anyone can interact with the blockchain however they want. We should basically assume that clients can and will be hacked. In fact, botting is basically guaranteed. So these constraints are a little bit restrictive, but under them, this gives a lot of opportunity for building some really cool stuff, provided that we like think in terms of the constraints. So we have these design pillars that we've come up with. The first is that we want to design around the blockchain's constraints. So we don't want to just like build a game and then say, oh yeah, here's an MMO, and by the way, there's blockchain. We want to build like a native like blockchain game. So what does this mean concretely? First of all, it means that moves can take on the order of like minutes to hours. So we're basically building kind of like pseudo idle game where you can like check in every few hours and you can like rearrange you can manage your troops, kind of in the vein of like Candy Crush. And this is because if we build a game where moves take on the order of seconds, this just like doesn't make any sense in terms of the block times, because that would just mean that your moves just don't sync up at all. We also want to lean into procedural generation as much as possible, because this means that we don't actually have to hold a lot of the data on chain. It means that we can say, for example, we can hold an ID on chain or like some set of state, and then we can grab the state off chain, and then we can derive all the values that we need using procedural generation. And we also have this little lazy updating trick that I'll talk about later in this presentation. The second pillar is that we want to embrace bots. We don't want to like fight against them, because there's basically nothing we can do to prevent people from botting. So what this means is that there's two specific things. First is that resources are local. So what we mean by local resources is, well, for instance, we have a currency in the game called silver, but silver, unlike gold in a traditional MMO, like it's not global. So if you grow silver on one planet, if you want to move it to another planet, you actually have to physically move it across the universe. You can't just, it's not the case, whoops. It's not the case that you can just grow silver in one place and you have access to it everywhere across your empire. Also, the universe has a fixed speed. So if you want to move 10,000 units across the universe, it's going to take 10 times as long as it would take to move 1,000 units. And what this means is that even if you have access to bots, this means that you're still constrained by the laws of physics in the universe, essentially. So the attitude here is we want to make sure that when we add mechanics, we're not really thinking of them as mechanics. We're coding the physics into the universe, and then we're allowing people to play the physics. So we basically want to build systems that are robust so that even if you are given infinite resources and you have a bot and you're trying to maximize things, there's still certain laws of physics that you're constrained by. And the last thing is that we want to allow players to design their own experiences. So because so much of the game lives on the client side, so basically all the cosmetics and just like most of the user experience lives client side, whereas the contract is really just like this kind of abstract data layer. This means that we want to lean into this ecosystem where we're likely going to have like lots of different clients, and we don't want to fight against this. It's very likely the case that someone's going to write a better client than we do, but we want to like provide, like, we want to build a game where this is actually like encouraged and this is fun. So let's talk a little bit about like, so now I just want to talk about like what this concretely looks like. Well, the first thing is that we have this universe metaphor in the game, which Brian mentioned a little bit, but basically like the reason why we use the universe metaphor is because we think that it's a very like natural construction from the constraints that we have given everything about zero knowledge, etc. So first of all, locations are sacred. So your location basically like is a first class citizen. It's one of the most valuable pieces of information it's one of the most valuable resources you have. It also means that we're trying to build physics over mechanics, and this is why it makes more sense to talk about this in terms of a universe rather than like a world like WoW, where you can just like walk around and explore things. It makes more sense to think about this in terms of like, or at least as a natural metaphor for the player in terms of like planets, and planets are hard to find. And the last thing that's interesting is that we also have these like meta games that will evolve from communities involving the information. So for instance, we added Twitter integration into the last version of Dark Forest. And this means that all sorts of interesting dynamics can come about based on the fact that we have physics and we have locations being the first class citizen. So for instance, if we want to target Brian, I can say something like, hey, I found Brian's planet over at like 127, 429. And this means that anyone else who like wants to fight against Brian, like I can basically send the universe against him if we believe that he's a threat. Alternatively, I can broadcast some unclaimed high-level planet. And what this would allow me to do is maybe I know that Brian is nearby this planet and he might really want this planet. This might mean that I can like influence or predict his behavior. And the last thing I can do is I can so for instance, suppose Brian and Singer are like two very high level players and everyone can see their names on the leaderboard. I can broadcast that they're fighting somewhere. I can basically invite the rest of the universe to come watch, or maybe try to like get in and interfere with their interactions. So now I want to talk a little bit about how we're using procedural generation in the game. So procedural generation, basically the principle here is that we have like some small set of data, or we have some state and a small set of rules. And from this, we try to generate infinite content. And one of the best examples of games that do this is Minecraft, where basically in Minecraft, every world is different, every world is unique, but you still have a set of rules that kind of tie them together and make the gameplay experience cohesive. So the first thing we do is that every planet is identified by a unique planet hash. And what this means is that we don't actually need to store everything about the planet on chain. We can store most of it. We can allow a lot of it to be derived. So the hash is essentially, we can think of it as like a sequence of bytes. And the first 2 bytes, which are like the 0000 bit, is basically what proves whether or not the planet is actually a valid planet or not. But then we can chop off all the bytes that come after this, and we can use this to derive all sorts of bits of information. So for instance, from this, we can like derive the planet's like population cap, the growth, the silver cap, etc. And we can actually derive this off chain instead of on chain. And therefore we don't have to waste gas on storage. So the other thing, the other big thing in terms of procedural generation is that we want to have some sort of like variance in the universe so that it's interesting. And this is a diverse and meaningful content. So it turns out that in a game like Minecraft, and actually in most games, there's basically only like one really important algorithm that you can use to generate most of what you need. And that's called Perlin noise. And Perlin noise is very cool because it can fit into it's easy to put into zero knowledge because it's almost all multiplication and additions. So here's an example of like how we could use Perlin noise on the client side, for instance, is that like, so the general property of Perlin noise is that it's globally random and locally smooth. So it means that if I move 1 pixel to either side, I can guess that I'm mostly going to be in the same neighborhood. But if I move 1,000 pixels away, I don't really know what it looks like. And we can generate these kind of planetscapes in the vein of Minecraft or Terraria, essentially using Perlin noise. And what this means is that in the previous example, we could have like oceans and deserts. We can have some places where planets are more valuable, some places where they're less valuable, etc. So I just want to talk a little bit about the Perlin noise algorithm to show like why it's so convenient. So for Perlin noise, we basically divide the 2D universe into a bunch of grid cells. And at the corner of each of these grid cells, we define a gradient vector. And this gradient vector represents the gradient of the three-dimensional surface at that point. So now suppose we want to query for noise of xy inside of this grid somewhere. So what we do now is we generate these difference vectors between that point and every corner of the grid. And then all we do is we take the dot product. We take the average of the dot products of each pair of, for each corner, we take the pair of the difference vector and the gradient vector, and we take the dot products, and then we take an average. So all we have here is we have dot products, we have a weighted average. So these are all just multiplications and additions, and this is really easy to fit inside of a snark. So to give an intuition for why this works, let's suppose that we want to maximize the magnitude of Perlin noise. And in order to do this, we'd have to have all the dot products be maximized. And this means that all the vectors are parallel to each other. So what might this look like? Well, so this means that if the gradient is pointing outward at all points, then this is a peak. So when the magnitude of the Perlin noise is maximized, then this shows that we just have like a peak or possibly a valley in the surface. So we can reiterate this process over an entire grid, and this allows us to give a pretty natural and decent looking form of noise that we're looking for. And you can see that we have the properties of global randomness and local smoothness, where if you start at one point and you move slightly to the side, then it's still going to be smooth. But if you try to, if you start at one point and then you look on the other side of the grid, then you don't really know what it's going to look like. So why is this cool for us? Well, this allows us to add meaningful variation in the universe. So as I mentioned before, you could have like parts of the universe that are high density or parts that are low density. And this means that you can have territories that people fight over because people know that there's a certain region of space that's just like much more valuable. Or maybe you can even add choke points and whatnot. And the contract also doesn't need to actually know the Perlin function, which is the cool part about this. So we don't need to waste gas or compute in trying to store this Perlin function on the contract side, because all we need to do is calculate it on the client side. And because we have a snark, we can actually just submit to the contract and prove that we've done things correctly. And this also means that it doesn't cost us any extra storage. So it's a very like easy and scalable way to add a lot more meaningful variation and make the game much more interesting. So the other thing I want to talk about on the technical side of it is this lazy updating trick. So basically the problem is we want to build a real-time game, but we're on a blockchain. And this means that the blockchain state only gets updated every 3 to 15 seconds or so. So here's how we resolve this problem. We basically say that for every resource or for every value, we treat that value as a function of time and state. So what this means is we take the current time, whatever it is, and we take the state of the blockchain. And then from this, we derive the ground truth value. And on the client, we use date.now in order to get real-time updating. But on chain, we use whatever the block time is, because we only make contract interactions whenever there's a block tick. And whatever time that block is at, we use that as the time. So we basically have the ground truth, which is moving at real time, and then we have the chain, which is syncing every 15 seconds. So here's an example in terms of planets. Suppose we have planet A that has 1,500 population, and we have planet B that has 750 population. On chain, we store that planet A has 1,500 population and that planet B has 750. But we also store a list of events. So now suppose that we queue an event, and the event is that we want to send 750 population from planet A to planet B. So we subtract 750 population from planet A, and then we tell planet B that we queue an event and we also give it a time, and we say sometime in the future 750 population will arrive. So now let's suppose that we just wait like 4 hours or something. So on the client side, it looks like, so planet B has received the troops, and planet A its population has grown a little bit because planets have natural population growth. But nothing actually changes on the chain side. So as far as the chain is concerned, nothing has changed since the last time both of these planets were interacted with. And we can wait even longer for planet A to grow back to its max population, and still nothing changes on the chain side. So when do we actually make these updates? Well, let's suppose we have some mystery planet here, C, which we're just going to use for example. So whenever either planet A or planet B is interacted with, then we update that planet to its ground truth, and we sync it up with the current time. So suppose we queue a move from planet B to planet C. We're going to immediately pop the 750 arriving event from the stack, and then we're going to update the planet B's current population to 1500. Then suppose we want to send like 100 troops to planet C or something. Then we would update planet B using the we would subtract 100 from the updated population, and then we would queue that onto planet C as well. And then over time, this will sync up and everything will be matched up. So the same thing applies for planet A. So you'll see right now that planet A says it has 750 population, even though on the client side, it says it's 1500. And this is because planet A has updated and has continued to exist in the game world beyond the last time the contract has interacted with planet A. So suppose now we queue a move from planet A to planet C, then we're going to calculate the current population from the block time, and we're going to update planet A's population on chain from 750 to 1500. Then using that new calculated population, we would subtract 100. And that's the thing that's the move that the contract would see, is using the new population at the time that it's interacted with. So that's all I have in terms of game design. So if Brian wants to just wrap up and talk a little bit about where the project is going as well, then I will stop sharing my screen.
Cool. Yeah, so if you're interested in updates, we're on Twitter at darkforest_ETH. You can also join our Telegram group, which I believe is t.me/zk_forest, or subscribe to our mailing list, which can be accessed via the website of the game, zkga.me. We're looking to release the next iteration this month, so be on the lookout for, oh yes, I can send the Telegram in the chat. I believe it is this, ZK Forest. Okay. So yeah, join our mailing list or follow us on Twitter if you'd like updates on that. And there will be a number of sort of interesting updates. For those of you who played in the last game, we're adding in some fun new mechanics and general quality of life updates as well. If folks have questions, also, we'll be sticking around for a while. There's like a lot of stuff that we sort of skimmed at a high level, but there's also a lot of like interesting things kind of under the hood when we go into the weeds. So yeah. Oh, we have a question in chat. Question. So this is from Ilad. CPU power seems to be a big resource in the game. Isn't that a problem? So yes, it is true that if you have a like more powerful machine that can hash space faster, you will like simply know where more things are quicker. So computation is indeed like a first-class resource in the game. And this is one consideration that we have to balance around, thinking about like, you know, if someone is mining like 10 times faster than someone else, making sure that that isn't like a game-breaking kind of thing. But anyways, I don't know if, Louis, do you have like a usual procedure for taking questions at the end?
Usually, when we don't have spammers into the chat, we usually let anyone to talk. But I guess here in this context, we could have people. We usually take 5 to 10 minutes to ask questions. And I guess in this context, we could maybe ask people to put them on the chat so you can pick up and read them and pick them up.
Oh, cool. Great. Yeah, so if folks have questions, then please drop them in the chat.
Power thing.
Oh, yes. Mm-hmm.
So like this is kind of what I mentioned before in terms of like thinking about the universe in terms of physics. So here's a kind of contrived metaphor, but one that we've been using is that like, well, you know, in real life, we have like the hegemonic powers, which are like the United States and China and Russia, but this doesn't mean that like everyone else just like doesn't exist. So this is the kind of metaphor that we're using, that like we have some like super users who are going to be like, essentially like the United States and the China of the Dark Forest universe. But if we design the physics in a robust enough way, it should still be fun for everyone else to play, even if they are like, quote unquote, have like less resources or have like are worse players because of their CPU constraints. And this has been like decently successful in games like Eve, where you have like guilds who are essentially the nations, and then you still have small players, or even in RuneScape where like there's members and there's free-to-play players, but it's still fun for free-to-play players. So ideally, like we have some sort of like robust system where yes, more CPU power is good, but this doesn't actually matter for most players. It's still fun.
Cool. So our next question is from Prayush. Sorry if I'm mispronouncing. The question is, can you adversarially tweak the input to the Perlin noise generator because it's all computed on the client side? So there are two places where Perlin noise is being used, and maybe I can answer this on the sort of like contract/ZK side, and then maybe Alan, if you want to talk about like sort of how this fits in with the whole like clients can be, we can have like a bring your own client sort of system here. So the way that Perlin noise is used on sort of the data layer side is that we use it to give the universe texture. So in future versions of the game, Perlin noise can be used to make it so that the universe, like different regions of the universe have different properties. Maybe this is like an ocean with like very few planets, or like here's like a very rich hub with like a lot of planets. And what Alan was mentioning earlier about Perlin noise is a bunch of additions and multiplications. Basically the way that fits in is that like we put Perlin noise into the snark. So that way players are kept honest. Like you can't adversarially be like, well, this planet like is in a really high value area unless you actually are able to prove it inside of the snark. And then there's another place which we use Perlin noise, which is sort of the client side stuff. And Alan, if you just want to mention that.
Yeah. So earlier I showed that like little procedural planet graphic, and so we kind of have, this is a little bit what CryptoKitties does, where like a lot of the like all the cosmetic stuff is lives essentially abstractly on top of the contract. And what we could do, for instance, is like we can make some planets really valuable. So we currently have like some little Easter eggs that are hidden inside of the cosmetic side, and maybe in the future, as like the universe grows, hopefully this means that like these planets contain some sort of like value. Now, what this might mean in terms of like adversarial attacks is that you might be incentivized to like say that your planet looks like one thing, or that it has some sort of rare properties. So we actually want to encourage this a little bit, in the sense that what this means is that you could spin up different skins or different cosmetic layers on top of the core contract layer. So one really weird thing you could do is you could actually just reskin the entire game. You can make it a fantasy game with like princesses and dragons and castles. And we actually see this as like the general thing that this idea of like adversarially tweaking the input is pointing to. Even if like the hackery/adversarial version isn't like strictly good, it still encourages an overall ecosystem of like people bringing their own clients and trying to spin off different versions of Dark Forest that live on the same data layer. So this is definitely possible, and possibly even good if we manage it correctly.
Cool. Scott, do you want to take the next question? Let me unmute Scott real quick.
Awesome. So the next question is from Yasin. What are your thoughts on moving the game to layer 2 solutions? So so we're currently definitely exploring like skill-based solutions to like practically move our game away from like the testnet. The main contribution here is like going forward, we see that Dark Forest is very likely to be living in like this like layer 2 solutions because of like gas constraints that is happening on mainnet currently. So the main contributions that we really also have is like there's also like something that we actually learn during the experimentation of like Dark Forest is like how the game actually evolves with like the gas cost that's associated in like making the moves by itself. So we're seeing like a different like player dynamics when like gas prices are high, and like when gas prices are like extremely low, and like if it's like in like somewhere in the middle. So in that scenario, we really just like see it as like there's multiple contributions of like having a very low gas fees and how like it can influence like player behaviors. And we're taking that into considerations when we were also like designing the game. And Alan could probably speak more on this side as
well. Sure. So the thing that's interesting here is that we originally wanted to deploy to mainnet, and with those transaction fees, this is why we kind of had this model where like it's a little bit like Candy Crush in space, or it's like a kind of like idle empire builder game where you like check back in every few hours. So this is clearly not feasible. And the version that we deployed to the Ropsten testnet before, people actually engaged with quite a bit, and we had like massive volume, and people just like had a lot of fun doing that. So the thing that happens if we do move to layer 2 and we bring in and we're able to drive the costs down is that we can basically like lift or relax some of the constraints that we put on ourselves. And this might like allow us to meaningfully change the way that players interact, or maybe we can do cool things like batch transactions, so that you can like manage entire portions of your empire at once. And even though we're talking about this as if it's a contract side thing, well, for 90% of players, like the UI itself is the game. They don't actually care about the separation between client and server, which means that we actually could just like build a different game for different people, where maybe one version is like mass batching transactions and another version is not. Brian, maybe do you want to answer the volume question?
Oh yeah, and I'll just also go in order to make sure that all these get answered. One question is, what are we thinking about for this project over the next few months and beyond? Like Alan mentioned in his slides, we think it would be really cool to get a persistent world that can support infinitely many players onto Dark Forest. That's also, you know, and kind of like one of the appeals of blockchain gaming is that you can build these like economically backed worlds as well. So for those who are familiar with like EVE Online, if you could imagine, you know, an EVE Online on the blockchain with real crypto assets that are fungible and like everything is liquid, like that would just be amazing. And for now, sort of the last version of Dark Forest was almost a proof of concept of the ZK stuff, where, you know, we ran it as like a time boxed round that ended after a week. But getting Dark Forest to be robust to the point where it's like it can be an infinite world is definitely like one of the first things on our minds right now, though that's going to take a while. Oh, Lewis asks 2 questions. Regarding layer 2, are there ways for miners to influence the game? And also, what volume are we talking about? So first off, to answer the volume question, the gas used on the Dark Forest core contract on Ropsten at peak was exceeding the gas usage of all of mainnet, which is one reason why it is, you know, infeasible for us to put this game on mainnet due to the transaction fees. So in particular, just a little bit of a funny story, we actually had to ask a friend to spin up a miner on Ropsten and increase the block gas limit because otherwise it wasn't, you know, people were sort of getting like delays on their transactions and stuff. Regarding whether there are ways for miners to influence the game. So depending on the setup of the layer 2 solution, the answer is probably. We're not sure, or at least my answer is probably, but I'm not sure how at the moment. We currently don't depend on things like block hash, i.e. like we don't use that as like an insecure source of randomness. However, block timestamps are one place where, like, you know, if someone wants to like fudge something in 10 seconds one way or another to make like a move or an attack, like arrive with slightly more or less forces, this is possible. We've thought about this a little bit, and it doesn't seem like there's too much that you can do besides that. But we aren't ruling anything out, and we would actually be quite interested to see if there are attacks that people make on more complex versions of the game if we get there. Oh, related to censorship, yes. Miners can censor transactions. So we would hope to have like a layer 2 solution, ideally in the long run, that looks more like, you know, like optimistic or ZK rollup with a lot of validators would kind of be the ideal there. Okay, and then we have one more question from Leonard. It seems possible to mask coordinates, e.g. Commitment to 5, 20, what has been tried and what's not possible? Curious to know the limits of this hash-based ZK state machine. Yeah, so right now, one of the bottlenecks that we're actually running up against is the performance of ZK systems and sort of like in-browser proving systems. So right now, like the MIMC hash function, which we use, takes about like, a couple hundred milliseconds to generate a ZK proof for in browser for like most modern computers. But once we start getting some more complex constructions involved, like Alan mentioned, stuff like introducing Perlin noise into the universe, we're already at like a few like 1,000 milliseconds for generating proofs. And further than this, we're going to need to see like protocol level improvements or other sort of like fundamental research to start coming through to the production layer. Because right now, like ZK is not like the power of ZK is not sufficient to support like the truly like expressive and like very rich universes that one might envision in like the long-term future of ZK or blockchain gaming. We have a question on how to get an invite key to the game. Sign up for our mailing list at zkga.me. If you like scroll to the bottom, you can enter your email address, and we send invite keys generally over mailing list to mailing list followers. I'll let maybe Alan or Scott answer the next question, which is regarding persistence.
So, yeah, in terms of persistence, there's two things I think about here. The first is that like something that's really fun from like the UX perspective is like staking your claim in the world. So there was this little experiment that Reddit did a while ago, which is like /r/place, which maybe some people here are familiar with, and the setup was like, you have like, I don't know, like 8,000 by 8,000 grid of pixels, and that like every 5 minutes you can just like every Reddit user is allowed to like change one pixel. And what ended up happening is you got these like entire communities who try to like map out bits of the like world and like try to draw flags, and maybe like the US will try to draw like a massive like US flag. So if we have persistence, we can kind of tap into these mechanics where like the sense of community is much stronger if there is a persistent world. If people know that the universe is time boxed and it's going to like die within like 2 weeks, then they're much less incentivized to like essentially try to like stake out a little claim of the universe. And the type of player that this impacts most is actually not the advanced player, but it's the casual player. So most likely, like a lot of hardcore players are going to be happy just like trying to optimize the game and trying to win that way. But for casual players, well, now if they take even a tiny planet, well, this is still a meaningful thing in the scale of the universe because it is their planet. It is the planet that they own, and they will forever own this planet in the persistent universe. And this is super, super cool, kind of in the same way that like a lot of people just like bought a CryptoKitty or like a lot of random people just like bought 0.01 of a Bitcoin just so they could own it. So this like sense of ownership is much more powerful and meaningful if we have a persistent universe. And the other thing I think about here is that like adding on to this is a little bit more on the client side where, well, if we have like cool cosmetic skins, then you could say something like, oh, well, I found this really cool planet and now I'm the official person who owns the planet called Clown Town. And like, that would just be really cool. And this is like a much more delightful thing. It adds like a lot of, it adds a lot more kind of delight to the experience of exploring if you know that these things are like real in some sense. And this also means that you could trade them, and we could potentially have economies that like come up out of trading these things.
Cool. How would optimistic rollup work, as there are very strong incentives to send wrong transactions, especially since the game assumes instant state change? And also related, how do we handle reorgs? The answer is yeah, like we are unsure of how optimistic rollup would work here. It seems like we are obviously biased towards ZK in general, so we've been excited about and trying to follow along with the progress on ZK rollup, but that also seems a little bit far out. Regarding reorgs, we just follow the largest chain largely. So, at any point in time, if you refresh the game, we're just going to pull from your like MetaMask Web3 provider, what is the latest state of the Ethereum blockchain. And because like the universe is just like a function of what's in the contract at that time and the current time, you should always be able to get some consistent universe. Oh yes, regarding trusted setup, also on the circuit, for these test rounds, we have not actually done a trusted setup. So you'll just have to trust us that we like, ran the SNARK.js command and did not like mess with the default behavior and didn't save the toxic waste anywhere. For the persistent universe, we will have a trusted setup though, as you could imagine that like there might be economic value on that universe. Let's see. Oh, the other thing that I just want to quickly comment on all of a lot of the stuff that we've been talking about the last couple minutes is that a lot of this is like very, very speculative and just comes out of sort of our like, philosophizing around like, well, if we have a much like larger, more persistent or longer running universe, then like what might be some of the things that happen in this universe. We obviously like don't know for sure, and anything could happen. People could like not play the game. It's like very unclear. Oh, special treatment for reorgs on the UX side. No, we don't currently have any, and this might actually be one of the, we were like having some mysterious bugs this last round where people would notice that like some events seem to like be like dropped by the MetaMask provider. And one of our hypotheses is that actually this is a result of reorgs. In terms of moving to layer 2 solutions, this is actually like one of the advantages potentially, I think, of some of the proof of stake layer 2 solutions like XDAI, in that reorgs would not be as much of a problem versus like, in a proof of work chain. I believe there were some attacks on Ropsten where like thousands of blocks were reorged, and our UX currently does not have any like way to handle this. Cool. Another question is there money involved in the current version or the next ones? We had a prize pool of about 1,000 DAI for the last game that we sort of distributed manually to the top 16 players, and we might experiment with a few more low stakes, economic mechanisms or rewards where we put a prize pool on certain planets or things like that. And yeah, that's we'll have to look. We'll definitely have to like care a lot about security as economic mechanisms ramp up. But right now, the focus is largely on building like a robust and enjoyable game. And then another question from Alex: have we thought about how to monetize the game to support its development sustainably? Right now, we're all students, and our focus right now, most of our team is like taking time off to work on this, but one of the nice advantages of software is that it doesn't cost that much to make a game. So things like, grants and stuff like that. I mean, we want to hold, especially in like the early stages of development, to kind of a more like hackery or like open source-ish ethos. And while in the future, like, especially if we can get to like a persistent world, we might have to like think a little bit harder about things like sustainability or like venture funding or things like that. At the moment, through, this past summer and this early fall, the way that we're thinking about the game is largely like, let's make like a cool game for the crypto community. And fortunately, that's not too hard to do as far as like capital concerns.
Oh, one thing I will add in terms of monetization is that there's kind of like there's just a lot of possibilities here, which is kind of what makes this cool, is because so given like the amount of gas volume that we saw in the playtest, well, this means that people are already investing like meaningful opportunity costs just in like their own time, which means that like there's ways that we can we likely will end up like using some sort of microtransactions, partly just because we have gas fees, but there's also ways to like lock up economic value in very interesting ways. So like the ideal version of this is that like planets themselves just have value by virtue of people like caring about this world, or this world being persistent in some way. And then therefore like maybe people are like maybe we incentivize people to be like playing because like for them playing is kind of like a bet that they can make more money by playing the game, by like conquering valuable planets. And therefore, it's possible that we can have like very natural ways to essentially lock up economic value and essentially like keep this whole thing self-funded. But we have not actually implemented this or thought too hard about it.
Cool. Sweet. So we'll stick around for maybe a couple more minutes if anyone has other questions, but it looks like that's all that we've got in chat for now. I'll turn it over to Lewis.
Great. Thank you very much, guys. It was super interesting. To be honest, it's surprisingly cool what you managed to do with like such an early stage of technology. So congrats. I'm looking forward to for the V2 so I can participate this time. And no, out of that, it's pretty amazing. Yeah, thank you very much. It was a fantastic presentation. I want to thank also Alex for organizing it and presenting. And thank you so much for your time and energy. Can I ask an extra question? I recorded this session. Would you be able to share the presentation so we can distribute to our community?
Oh yeah, absolutely. And I guess we should also cut out the Zoom bomb at the beginning.
Yeah. That's actually was the plan. It was on the plan. And to conclude on that note, just for you to know, next month on the 8th, we will have. Sorry, my dog is popping down. The next month we will have another meetup with Coda, introducing the latest, like the Pico, if I go it correctly. Thank you very much, Brian. Thank you very much, Alan. It was very fun. Oh, there is an additional question before we conclude.
Oh yes. Let's see. So the question is, any broader thoughts on increasing entropy causing catastrophic changes on a persistent layer? Yeah, I mean, there's like interesting things that we could do that are somewhat in between persistence and like time boxed mechanics. So, you know, you could imagine like, you could imagine like some sort of like sub-universe or like mini event sort of constructions where like, you know, in some region, like after some period of time, maybe like all of the planets are destroyed or things like this. There's a lot of fun thoughts to bounce around here, but for now, we're mostly trying to focus on like what is possible with zk and with the Ethereum blockchain right now. Though there's a lot of opportunities certainly for like kind of fun and interesting bits in the future, or little like gimmicks or things like that. So.
Great.
But yeah, if that's all, then thanks so much, Lewis and Alex, for organizing and for having us. This was super fun, and we are reachable on Twitter at darkforest_ETH. So feel free to reach out if you have any other questions or comments, concerns, suggestions, etc.